Hi guys, hope you're having a wonderful day so far. Today we're going to talk about the last property that has trends on the periodic table that we're going to study this year, and that property is solubility. So let's first define what solubility means. So solubility is the ability to dissolve. Let's write that down. Ability to dissolve. And the solubility could be different in different solvents. So something could be soluble in water, but not soluble in acetone, for example. And so we're just talking about solubility in general. The most common solvent that we have is water, but it could be solubility for any of the other liquids or solvents. So to test our solubility, we're going to do a little demo. So we are going to look at magnesium, calcium, strontium, and barium ions. And you can kind of look at these and see what the relationship between them is. Hopefully you can tell that they are in the same group. They are all in group 2 on the periodic table. So magnesium, calcium, strontium, and barium. So we are going to test their solubility, like I said, and let me make my screen a little smaller. So we are going to take these ions. So the ions don't exist on their own. They exist as a compound. So when we say magnesium, it was really like magnesium nitrate or magnesium chloride. But the magnesium ion part is the part that we're interested in right now. These were all like magnesium nitrate, calcium nitrate, strontium nitrate, barium nitrate. These are all compounds that are solid at room temperature, but we have dissolved them in water. So we have solutions like this. And so I have my solutions here. So this is magnesium nitrate, the calcium nitrate, strontium nitrate, and the barium nitrate. And as you can tell, they are all clear and colorless solutions. So what I'm going to do next is I'm going to combine them with a different substance. So I'm going to combine them with a sulfate ion here, which I'm getting from sulfuric acid, H2SO4. The SO4 2- comes from here. I'm also going to combine them with chromate ion, or dichromate ion, I should say. So that's coming from the potassium chromate here, which is the solution there. So we're going to start with the sulfate with the sulfuric acid. And I want you, when I add them, to look to see, is it soluble? So if it is soluble, it's going to be like see-through, clear. If it is insoluble, that means doesn't dissolve, then we're going to see some cloudiness and some precipitate form. So this is magnesium, and I'm going to combine it with the sulfate ion. And hopefully you can see that it's still pretty see-through. So that looks like it's soluble. So this one right here we're going to say is soluble. Okay, I'm going to try same thing with the calcium. Add some of my sulfate ion. And again, it looks like it's soluble. Everything's dissolved. Let's look at the strontium. So here it is. I'm going to show you the other two just so that you can compare. Here's the magnesium and the calcium, and here's the strontium. Looks like it's cloudier, and so that looks like it's a little bit insoluble. I'm putting I for insoluble. This is barium, so let's add it. You can tell it instantly formed solids. So here they are in order. So this is magnesium, this is calcium, this is strontium, and this is barium. So you can see the trend as I go from magnesium to calcium to strontium to barium. It looks like it's getting more and more insoluble. We're going to do the same thing just to double check with this other ion, with the chromate ion. Now the chromate ion is yellow. So the color itself is not really going to help us determine whether it's soluble or not. They're all going to be yellow, but whether we form a precipitate, whether it's cloudy or not, that's what's going to tell us. So again, here's magnesium. And you can see it's see-through, it's pretty soluble. Calcium is next. Again, pretty soluble. Here is strontium. And it's hard to tell, so let's compare it with the other two. You can kind of see this one's a little bit cloudier than those two, so slightly insoluble here, getting a tiny bit of precipitate. Let's look at the barium. You can see that this instantly forms a lot of solid here. So again, I'm going to show you all four together. Here they are. So magnesium, calcium, strontium, and then barium. So you can see again, as you go from magnesium to calcium to strontium and barium, getting insoluble or getting less soluble, we should say. So the trend as you go down a family looks like the solubility is decreasing. We're not going to look at it across a period. We're only looking at it for solubility as you go down a group. So let's think about why that is. So when you are dissolving something, like let's say I take some water and dissolve some sugar in it. Well, what happens? Why does the sugar look like it disappeared? Well, there's a small amount of sugar compared to the water, right? So what happens is the water molecules surround the sugar molecule. So each sugar molecule is surrounded by a whole bunch of water molecules. And so to the naked eye, it looks like the sugar disappeared because each sugar molecule is surrounded by all these water particles. And so all we see is the water. So when you dissolve something, basically you're getting the solvent particles to surround your little solute particles, right? So why would it be that it's harder to get water or whatever solvent you have to surround your solute as you go down a group? What do you think? Well, if you're trying to surround something, the smaller it is, the easier it is to surround, right? So as you go down a group, your atomic size increases. So the size of your atom increases, and so it's harder to surround it with water or with whatever solvent particles you have. That's really pretty much it. It doesn't have to do with Zeph directly, kind of indirectly, because as you go down, Zeph decreases, your size increases, and so it gets harder to surround and gets harder to dissolve. So let's write that down. As you go down a group, the size of the atom or the atomic radius increases, so it is harder to, or let's say for solvent particles to surround the solute particles because they're larger now. So harder to dissolve, and therefore your solubility decreases. Okay, again, we're not going to look at it across the period. So that is it for the trends. I do want to mention that in our packet, you will see the last couple of pages of the packet look like this. It's called Periodic Properties Summation Sheet. And there's 2 pages to it. Yours is not filled out, but this one is. So this one that's filled out is posted on Schoology if you want to refer to it. But I think this is a really good reviewing tool. You put what property it is, you put the definition, the trend across the period and why, the trend down a family and why, and any peaks and valleys that you see. So I think this is pretty valuable way to review, so I would recommend that you review that and do that and check with the key on Schoology as well. Last thing I'll mention is I do want to show you real quick a little trick. So I want you to understand these trends and these properties, what they mean and why. And really the key to them is Zeph, right? Once you understand what Zeph means and what the trend is, you can come up with all these other trends for all the different properties. But let's say you're on the test, you're taking your test and you just like blank out, you don't remember how to do stuff, what increases, what decreases, it gets confusing. Think of a one-armed snowman. So a snowman that looks like this. One-armed snowman. Okay, so I'm going to draw this on the board, one-armed snowman. And the snowman represents the trend for size and metal reactivity. So let me show you what I mean by that. So draw a snowman with one arm. Snowman. Size and metal reactivity. This is the trend for the size and the metal reactivity. What does that mean? It means as you go down, the size of the atom increases. As you go across, the size of the atom decreases. So it follows a one-armed snowman, right? So that is true for size and also for metal reactivity. Metal reactivity increases as you go down, decreases as you go across. All the other trends that we've talked about. So let's see what we talk about. Ionization energy, electron affinity, electronegativity, Zeph. All those trends are the opposite of the one-armed snowman. So the snowman, S and M, size and metal reactivity, all the other ones are the opposite. So all the other ones decrease as you go down and increase as you go across. Hopefully that's a little tip to help you. You know, if you are taking your test and you're desperate and you don't remember what the trend is, this is not going to help you figure out what the reason is, but it'll help you remember the trend. Hope this helps. See you guys. Bye.